Here's another example for class 22. I believe this is the one that I went over in class. It's one from Schaum's outlines, and I think of this as a kitchen sink problem because it's got just about everything going on for it. In this position that's shown, this block A is moving downwards at 1.5 meters per second. So that means that everything else that's attached to it is also moving, including this cylinder, and it moves in a frictionless bearing. And we presume that this rope on there, it doesn't slip. So it is actually making this pulley or the cylinder rotate, and it's pulling block C along with it. The spring that's attached to block C is originally compressed by 150 millimeters. That spring has a modulus, aka spring rate or a stiffness, of 80 newtons per meter. And we want to find the speed of A when it has dropped down 1.5 meters. So we could probably, if we were doing this, if I hadn't already done this, I would maybe draw this. Maybe I'll draw it as a ghost, right? Or a dotted right here. Boom, boom, boom. Okay. And this too is going to be moved a certain distance here after a certain amount of time has elapsed. It's going to move this distance right here. We want to know what the speed of this is. It does have a speed to start with, right? So this is the big equation that we're going to use. It's good to stick this at the top. If we do, if we're starting, we know you need to use work energy to get this right out of the way so we can start thinking our way through this. Some stuff to get out of the way as well in the beginning is to make a kinematic relationship that we know that omega b is related to the velocity of A by dividing it by the radius of 150 millimeters. We also know that velocity of C is equal to velocity of A. We might want to go ahead and get the moment of inertia of B, get all these things out of the way. We know for a disk it's 1/2 mr squared, so we have this 0.99 kilogram meter squared. So going down, and we start to populate this thing going out here. So we start out with kinetic energy, and it's going to be the translational kinetic energy of A, the rotational of B, and the translational of C, because they are all moving. So we shove some numbers in there, and we have 295.9 Newton meters. We also, by the way, substitute right in here for this omega B. So, okay. And we have the potential energy to start with. Well, right here we'll say that this is the datum right here, okay? So for the gravitational potential energy, it's going to be ma g, and then h is going to be the delta y at A. We also, the spring is compressed some, and you'll notice that whether it's compressed or it's stretched, it doesn't really matter because it's squared, right? You could make that a negative number if you'd like, but it's squared, so it's going to stay in there. And then we have the kinetic energy so I didn't actually put that in. Actually, that should be a PE. Okay, so I obviously copied and pasted and didn't fix that. So let me write that down somewhere for future editions. Oh, you know what happened is on my sheet here, I use the T's and the V's that the book uses, right? So I had to be careful. So potential energy and kinetic energy, because I never thought it'd make any sense at all to have T as being something to equal kinetic energy. But that's just me, man. Well, maybe it's not just me. I have a lot of other books that Graffiti's used it, but it's pretty common. All right. So let's see. Yeah, it looks like I did this twice for some reason. That's weird. I wrote this out. Okay. So we got the answer. 860.3. And then the energy, external energy that's going on here is going to be negative because it's the friction force and the distance it moves. Now you can think of those in two different ways. One is that the friction steals energy away from the system, or you could think that the friction force and the delta x are in opposite position because the friction force is kind of moving that way, but then the motion is going that way, so they're opposite from each other, so it's negative. And I forgot previously to stick a delta x into there. It's right here, but I forgot to put it in there. And then I also forgot to put it into the number. So we get a negative 342.7. And then for the kinetic energy at 2, and here's like another mistake right there. That should be the kinetic energy of 2 at state 2 is going to be 1/2 ma va2 squared plus 1/2 I b omega b2 squared and 1/2 mc vc2 squared. And we know that vc2 is going to be equal to va2. So I should have said VC2, yeah, and VA2. And I also know that omega B2 is going to be equal to VA2 divided by 0.15. So we plug all those into there. And once again, you are wrong. Welcome to Wrongsville. And then we get the potential energy when we're done. Because we're at the datum, it's going to be entirely due to the spring stored energy. And that del 2, because it's been compressed, to start with, and then it's going to be stretched, right? There's going to be some spot right here where there's zero amount of where it's going to be at its free length, right? It's rather short right here. So we know that it's going to move a total of 1.2. So we take 1.2 and we could subtract it out here. And I don't know why I put 0.15 minus 1.2. Doesn't really matter. It's going to be a negative number here, but then we will square it. So then we get with the spring, it's going into tension, but we still have energy stored, right? And so here I've plugged everything back up into our main equation up here, and I can solve for VA2, which is the thing I wanted to get. So 2.42 meters per second is the answer. And notice they asked for speed, so we don't give a direction with that. And that's the problem. You can see the idea. Most important thing is to work through this problem, this equation, and then start trying to populate it and account for all the things that are actually taking place. Today's guitar is brought to you another black Gibson. I do like black Gibson guitars. And here is Les Paul Special. Okay. And so the Special and the Les Paul Junior, now this is not an old one, but there's also a cheaper version where they didn't do the wood fill onto it, so it leaves a lot of grains showing. But the Special was sort of actually made for a kid's guitar, right? Well, the Junior was a kid's guitar with the name Junior. A Special just meant that they had two pickups instead of the single one or the one. And some years the Junior was a single cut, and so it was more of a shape like a Les Paul. For a number of years they did the double cut, and I always liked that look a lot more than the single cut. But punk rockers used to start buying these things up. They weren't very expensive, but you could buy a vintage one pretty affordably, even into the 90s. Then eBay started really exaggerating the worth of the vintage guitars. So this is only like 20 years old or so, which isn't really old for a guitar anymore, but. It's a fun guitar. It has P90 pickups in it, which are single coil. They were the predecessor. Gibson came out with the humbucker in 1957. Seth Lover is the name of the inventor of the humbucker. And they came up with humbuckers, and most of the guitars kept having them. But the single coils predate those, and these were a much stronger pickup than the Fender single coils. And so they had a certain kind of a girth to them, and a bite that the humbuckers are like warmer pickups. So but Paul Special. It's a cool guitar.